Good morning and welcome, or good afternoon, wherever you might be. This is a tutorial on our subject today, which is remove and replace radiators. This subject is one of the units required to complete the AURTTC004, the Certificate 2 in Automotive Vocational Preparation. So I'm just going to share a screen with you now to explain the course instructions and the introduction to our course. So just this share right now, you should be seeing some instructions on your screen. To complete this unit, you'll be required to complete any prerequisite units. There aren't any in this case. Join the virtual class or the recording, which you're most likely watching now. Access and complete the learning resources and activities. You'll do that through the college cloud. Once done, download and save the assessment tool to your computer. Then after it's been downloaded, complete those assessment tool theory questions, then upload your assessment tool for your trainer to assess. Then after that, attend the college to complete any practical assessment if required and when possible. Just go on to the next stage, just an introduction to the unit. This unit describes the performance outcomes required to remove and replace the radiator of a vehicle. It requires a learner to plan and prepare the task, remove the radiator and inspect its associated components, replace the radiator, top up the cooling system and check for leaks, maintain the work area, tools and equipment. It applies to those undertaking VETIS training in schools or pre-vocational qualification as preparation to entering the automotive service and repair industry. So we're going to start today with a PowerPoint presentation on this particular unit. And as we can see, here's our PowerPoint presentation there. I'll start on the first couple of pages, remove and replace radiators. I think you all, or you may know my name's Andrew. I'm a automotive trainer, one of the automotive trainers here at the Gold Coast Trade College. I have significant years of experience in the automotive industry, and yeah, I should be able to answer any of your questions. Just on to some general information. You're watching this video, you're not actually at the college, so we do discuss when you are at the college some general information such as mobile phones, personal protective equipment, evacuation procedures, class durations, break times, code of conduct and student handbook as well. So we're not really covering those online. Just to run over our course objective today as well. Prepare to remove and replace the radiator. Safety and environmental requirements are sourced and interpreted. Task instruction is interpreted and vehicle radiator to be worked on is identified. We're going to be considering manufacturer's specifications, workplace procedures for radiator removal and replacement, potential hazards and risks associated with the task and reported to the supervisor. Tools and equipment required for removing and replacing the radiator are identified. And of course, manufacturer's specifications are identified as well. That's our preparation. Then actually removing the radiator itself, tools and equipment required are selected and checked prior to use. Vehicle is prepared for removal. Vehicle radiator is removed and associated components, including the radiator, are inspected according with manufacturer's specification, and results of those specifications, those inspections are recorded. So that's a little bit about our course objective. We're going to start with a stay safe, which is something we always consider. It's a very important part of any workplace. Wearing the correct personal protective equipment, follow instructions, policies and procedures, use equipment and tools correctly, consider your own health and well-being, observe any signage and take heed as to what that signage is telling you. Manual handling techniques are important, such as heavy lifting, and keep others safe and look out from one another. We all have a personal responsibility when it comes to safety. In your workplace, an employer has also similar responsibilities. It is the employer's duty to provide employees with a safe and healthy work environment. Under the Work Health and Safety Act, employers must assess risks and implement review control measures to prevent or minimise exposures to risks, identify hazards, determine who might be harmed and how, decide on control measures, put controls in place and review those controls regularly. So WorkCover Queensland provides details about risks and how to reduce those in specific industries. So as an overview, both the employer and the employee have certain responsibilities. Workplace health and safety. It all goes together with workplaces, certain responsibilities of employers and employees. Obviously, safety is very important. In an automotive workplace, we always deal commonly with hazardous substances and chemicals. There's many different types of chemicals present in a workshop, especially vehicle emissions, paint fumes, welding fumes, there's potentially asbestos, batteries, acids, lead, solvents, petrol, gas, dust and powders may also be available or found in our workshop. So safety procedures address the health risks associated with each of those hazardous substances, as well as issues around the correct storage of dangerous goods to prevent fires and explosions. Matching personal protective equipment to the hazard, such as choosing gloves with the right coating, is vital to your own safety. Along with safety considerations, we have environmental considerations. We're talking specifically about engine coolant and radiators. So specifically, engine coolant poses contamination threat to the quality of local water resources. So in short, we don't want engine coolant entering our waterways. Engine and corrosion inhibitors in bold, you can see on that PowerPoint there, on that slide, those corrosion inhibitors and coolants are now prohibited under environmental protection regulation from discharge to the environment. So if you discharge coolant into the environment, you are making an offence. Significant penalties apply to any person who contravene those regulations. So in terms of a workplace, facilities should be constructed and managed so that coolant cannot escape into the environment during normal business operations, or due to equipment malfunctions, or during emergencies such as storms, fires, or vandalism. Stormwater and runoff from roofs and external paved areas should be diverted away from the workshop and diverted away from chemical and waste storage areas. If you want to know a little bit more about the types of coolant you might be dealing with and some of the specific concerns around safety and hazard identification when it comes to engine coolant, we would need to consult a safety data sheet. Here's an example of a safety data sheet. Now I'm just going to scroll down to the next page and you'll see the actual safety data sheet on a particular antifreeze coolant. So as you can see, this data sheet starts to explain, it's many pages long. It explains a lot of information about this particular coolant. But I just wanted to cover a few of those hazards and risks. You might see hazard identification. It's classified as hazardous according to the globally harmonized system of classification and labeling of chemicals. It is acute toxicity, oral category 4. So of course, if you ingest this orally, very, very toxic. Harmful if swallowed. So it's something that we, of course, don't want to ingest into our system. Precautionary statement, prevention, wash skin thoroughly after handling. Do not eat, drink or smoke when using this product because it is flammable as well. As we sort of touched on, if ever you need to know anything about any particular material or chemical in a workplace, we need to consult the safety data sheet. There should be one of these data sheets on every chemical in your workshop. So if you're concerned or don't know what's in that particular product, consult this sheet. Rinse mouth, if swallowed, call the poison centre. So these sheets explain to the reader exactly what you should do in certain circumstances, such as inhalation, ingestion, having it on your skin, getting it into your eye, and advice to a doctor as well. Also talks about firefighting measures. What sort of fire extinguisher would we use if we had a fire around or caused by this particular coolant? You would use a carbon dioxide dry chemical, water spray or foam fire extinguisher. Do not use a water jet. Under fire conditions, this may emit toxic and or irritating fumes. It goes into quite some detail as to how you should fight a particular or that particular fire. It goes into accidental release measures, emergency procedures, wearing personal protective equipment, remove all sources of ignition, stop the leak if safe to do so, increase ventilation. Section 7, handling and storage. So there are procedures here for handling and storage this particular product. Conditions for safe storage, including any incompatibilities. What that means is there another chemical that should not be placed near this particular chemical? That's covered here as well. Storage regulations. There's an Australian standard. When it comes to storage regulations, there it is right there, Australian Standard 1940. Section 8, exposure controls and personal protection. Occupational exposure limit values. So there's a certain amount of exposure that you can bear, and after that it becomes over the limit. Ethylene glycol is the harmful product within this product. There's some more details on the vapor that's released from the particular product as well. Engineering controls, respiratory protection, eye protection, hand protection, and body protection. Might be worth just covering this hand protection. Wear gloves of impervious material such as neoprene or PVC. So you can pick up any pair of gloves and put them on, but you need to make sure that those gloves are going to protect you in the case of contact with this particular product. It does say that you need to be wearing neoprene or PVC gloves for this product. A little bit about its chemical and physical properties, and some other technical information there as well. Some of the symptoms that you might be getting if you do swallow or ingest this product. Symptoms from inhalation may cause irritation of the nose, throat, and respiratory system. It goes on to talk about skin, eye, respiratory, skin, germ cell mutagenicity, mutagenic hazard. Well, it's not considered to be a mutagenic hazard, not considered to be carcinogenic, not considered to be toxic to reproduction. So it does go into all of the issues around this product in quite significant detail. So it should really leave nothing or no question unanswered once you've read that entire document. So back to our PowerPoint presentation. That's a little bit of our material safety data sheets, or now known as SDS, a safety data sheet. So with all that in mind, there are procedures when handling coolant. There are precautions to be taken. It goes without saying, eye and face protection. Wear tight-fitting chemical splash goggles or a face shield. Always wear hand protection, chemical-resistant, impervious gloves, complying with the approved standard. We read that in the document. Ensure coolant is contained and disposed of correctly, and clean up spills quickly, and do not hose coolant down the drain. All right, on to the cooling system as an overview. This image gives you a quick sort of overview, cutaway version of a cooling system. And of course, typically an automotive vehicle has a radiator at the front, although it may not be in the front of the car. In some cars, it could be on the side or to the rear of the car. Some cars are even air-cooled, such as your Volkswagens or Porsches, I think. Most of the time you'll see a radiator at the front of the car. Behind the radiator is a fan. That fan is driven from the engine, draws airflow through the engine when the car's moving at slower speeds. We of course have radiator hoses, top and bottom. The water flows through the radiator hoses to the thermostat, just at the top of the page there, and then through the engine and back into the radiator again, thus cooling the engine. There's a couple of different types of radiators, downflow and crossflow. So subtle, or not subtle difference, pretty big differences. You can see by the diagram at the top, the downflow radiator. That's this radiator at the front here, has a tank on the top of the radiator. These black sections are called the radiator tanks. So there's a tank on the side for a crossflow and on the top for a downflow. You can also see that the vertical fins are evident on a downflow radiator, and the horizontal fins going that way are evident on a crossflow radiator. Those fins are hollow. Water flows through those fins as it continues down the radiator in its path. So you can see the red circles we've got here. Water comes in the top, flows down the radiator and out the bottom. On the crossflow radiator, top left-hand side comes in, bottom right-hand side, it goes out. So slight differences there. I'm just going to do another share now. We're going to have a quick look at a video on cooling system and cooling system principles. So this is an Automate video. Some of you may have seen these videos, but this is a worthwhile video to watch and understand a little bit more about cooling system and how it all works. So enjoy this video. I'm just going to share that screen now. Hope you can all hear that. I may stop the video from time to time just to discuss or cover a certain point.
The internal combustion engine converts chemical energy into mechanical energy with the byproduct of heat. Controlling this heat is the job of the cooling system. I am Clint. Welcome to Automate. We need heat in the engine to achieve thermal efficiency. The correct amount allows for effective combustion, while too little or too much will cause engine damage, high emissions, and poor fuel economy. The heat energy in an internal combustion engine is created from the combustion of oxygen and fuel. Regardless of the fuel type, high combustion temperatures need to be controlled. Excess heat energy must be removed from the combustion chamber. There are three types of heat transfer principles used in an automotive engine: conduction, convection, and radiation. Conduction refers to heat transfer through a solid. We can observe this in the combustion chamber. Heat from combustion of the air and fuel mix is absorbed by the piston crown. The heat then transfers to the piston rings and cylinder wall. In an air-cooled engine, the heat transfers to the cooling fins. Remember that heat always travels to a colder object. The principle of convection relies on heat transfer through a liquid or gas. When heating a liquid in a container, the heat will transfer through the liquid, rising to the highest point. This pushes colder liquid to the heat source. Heat radiation is easily seen at the cooling fins of an air-cooled engine. As the heat from combustion travels through the fins, it transfers to the passing airstream, using the principle of radiation. Air may still be used as a cooling medium, although in the modern vehicle, liquid is much more common. Air-cooled engines require cooling fins on the outer cylinder. These distribute the internally generated heat over a much wider area. Airflow over these fins removes the heat energy. Some OEMs may use a ducted fan to circulate air. In a rear-engine vehicle, this is very important, as the engine is enclosed and does not sit in the main airstream.
That's what I was talking about a little bit earlier. You can see that particular car, that particular engine, I should say, is air-cooled. Has a fan that's run directly off the crankshaft. So whenever the crankshaft's turning, the fan's turning and blows air through, over and across those cooling fins, therefore cooling the engine. So in that scenario, there's no water and there's no radiator, just a fan. A little bit like a two-stroke motor that you might find in a motorbike or a whippersnipper or a lawnmower.
Liquid-cooled systems are much more efficient at removing heat energy from the engine components. Heat transfers from the cylinder board to cooling jackets, which are cast into the cylinder head and block and contain the liquid cooling medium. The heat will transfer through the medium, travelling to cooler parts of the system, but manufacturers use pumps to efficiently circulate the liquid.
So we can see here that water comes out of the engine. This section here is the thermostat, through the thermostat, through the top hose. This is a downflow radiator, so the water flows down. As it flows down, it cools as air is passing through the radiator, cools the hot liquid, and that liquid then returns through the bottom hose back into the engine, only to be heated up again.
The now hot liquid exits the top of the engine and is pumped into a radiator tank. The radiator is placed directly into the airstream, where it is exposed to a moving air supply. As the liquid is pushed through the radiator, heat energy is given off to the passing airstream through radiation. The now cool liquid is drawn into the pump and pushed back into the cooling jackets, and the process starts again. Water was initially used for cooling an internal combustion engine, but due to its high freezing point at 0 degrees Celsius and low boiling point of 100 degrees Celsius, engine mechanical tolerances demanded the need for wider operating temperatures.
So this is a key point here regarding operating temperatures of engines, and also the function and the purpose of coolant. You've often heard coolant called antifreeze. It does a couple of things. It does three things in general. One is antifreeze, so it doesn't stop freezing. However, it makes the freezing temperature of water less than 0 degrees. So at sea level, water freezes at 0, boils at 100. Antifreeze will make it freeze at lower than 0 degrees. And it will also won't allow boiling at 100 degrees. It'll increase the boiling temperature. So it means the motor can operate in a wider range of operating temperatures and not boil or freeze the water in the system. I say water, but what I mean is coolant and water mixed. The third thing that coolant does is inhibit corrosion. So it's antifreeze, anti-boil, and it's also a corrosion inhibitor. So it does a lot of good things for a motor.
Replacing water with a manufactured product is one way to achieve this. Modern vehicles use purpose-designed coolants that are vehicle and manufacturer specific. Coolant is a mixture of chemicals such as ethylene and propylene glycol and distilled or deionized water. Glycol keeps the freezing point low and the boiling point high. Inhibitors are used to prevent corrosion, erosion, and reduce the foaming of coolant. Coolant is available as a concentrate, as it must be diluted with water up to a ratio of 1:1, or it can be supplied as a premix when no additional water is required. Mixing different types of coolant can have different outcomes. Some corrosion inhibitors might lose their effectiveness when mixed with other types of antifreeze, which may lead to engine failure. Another way to widen the operating temperature range of the engine is to raise the boiling point of the coolant. This can be done with a radiator cap. Increasing the pressure of the cooling system will raise the coolant's boiling point. For every 10 kPa of pressure increase over atmospheric, which is about 103 kPa at sea level, the coolant's boiling point will be raised by 2 degrees Celsius.
So this is a key point as well. A radiator cap on your radiator keeps pressure within the system. It's a little bit like a lid on the top of your Coke bottle. If you shake up your Coke bottle, the lid contains the pressure inside that bottle, the same as your radiator. So as your engine heats up, water and the engine starts to warm up and get hot. As things get hot, they expand and pressure increases within that system. Without the radiator cap, there'd be no pressure. Pressure increases the boiling point of water. So we've got a double effect here, the coolant and anti-boil effect of the coolant of the mixture increases the boiling point, so does pressure increase the boiling point. So every 10 kilopascals of pressure increase increases the boiling temperature by 2 degrees. So that further allows a motor to be operating in a wider temperature range and stops boiling.
A radiator cap stamped 90 kPa will raise the pressure within the cooling system to around 190 kPa at sea level, which will in effect increase the coolant's boiling point by 18 degrees Celsius. If the engine heats up and temperature increases, the coolant will expand. Because the cap is effectively sealing the system pressure also rises. The radiator cap will act as a safety device when a predetermined pressure has been reached. When the system pressure is greater than the force of the mainspring, the control seal is lifted from its seat.
So you can see in this diagram, as water pressure pushes upwards on this valve, overcomes the spring, water then would leak out or expel from the radiator. Because a radiator and a cooling system is a closed unit, we'll see from this diagram that that water then flows to the overflow tank.
Coolant exits via an overflow port and is pushed to the expansion tank. As the coolant pressure drops, the mainspring pushes the relief valve closed, and the system is able to build pressure once more. If the engine was switched off at this point and allowed to cool, the coolant within the sealed system will contract. This contraction causes a pressure drop at the base of the radiator cap.
So a radiator cap has two valves. It has one valve to allow the radiator to hold pressure and then let any excess pressure off. That's this large spring that you can see there in blue. And as the coolant cools down, once you've turned your car off, parked it in your garage, it cools down. When the hot water cools, it shrinks in size and creates a low pressure. So it's significantly less pressure. This lower valve here on the bottom of the radiator will open as that pressure draws downwards, and then allow some of that water to come back from the overflow tank back into the radiator as well. So it lets pressure off and also allows some of that fluid to reverse flow back into the radiator.
A vacuum valve built into the cap is pulled from its seat by this low pressure. A pathway opens up to the reservoir and coolant is drawn back into the system until the pressure reaches a balance with atmospheric levels. At this point, the valve will close. Removing a radiator cap from a hot engine is extremely dangerous. As the coolant exits the system, it loses pressure and converts to steam. Its temperature remains high and will cause extensive burns to any exposed areas of skin. Ideally, a system should be left to cool. A thermostat is essentially a temperature-controlled flow valve. It may be located in the engine coolant outlet or the water pump inlet. Its role is to regulate the flow of coolant to the radiator. The thermostat sits in a housing submerged in coolant. When the engine is cold and the thermostat is closed, a small amount of coolant is able to bypass the thermostat valve and return to the engine. This prevents hot spots occurring while minimising the engine warm-up time. It's imperative that the engine warms up quickly to reduce cold start emissions and prevent sludging of the crankcase. The mechanics of a thermostat is very simple. A heat-sensitive wax and metal pellet is positioned inside a heat-conducting copper vessel. This vessel makes up the main valve of the thermostat. The valve assembly is supported by a frame and kept in the closed position by a return spring. As the engine warms up, heat energy from the coolant is transferred to the copper and then the thermostatic pellet. The pellet expands when influenced by the heat energy. This expansion acts against a piston, which then forces the valve to an open position. If the thermostat is fitted with the bypass valve, it will move with the main valve's operation, closing the bypass port. All coolant will now be pushed from the engine to the radiator. Low temperature coolant exiting.
So we can see as the thermostat gets hot, because it's in contact with water from the operating engine, as the water heats up, thermostat heats up, thermostat then opens and allows hot water to flow into the radiator, thereby cooling that water and further cooling the engine. So the thermostat is regulating the temperature constantly. It's constantly opening and closing, or partially opening and partially closing, to limit that flow to the radiator, thereby keeping your engine running at a steady temperature. Otherwise, the temperature gauge on your dashboard would fluctuate with the outside temperature and the loads and so forth that are placed on the engine. So a thermostat keeps it nice and steady.
The radiator will be pushed through the engine, finally reaching the thermostat. This coolant will absorb the heat energy from the thermostatic pellet, causing it to contract, allowing the return spring to close the valve. This cycle of operation is constant in a correctly functioning engine. Manufacturers designate the thermostat's opening temperature to work optimally with the engine design. Electronic thermostats have now been introduced into modern cooling systems and are controlled by the engine control module. Keep a lookout for our training modules on these. Radiators are heat exchange units used to transfer heat energy from the coolant to the surrounding air. Radiators may be designed as a vertical or cross-flow type, but their operation remains the same. Hot coolant exits the thermostat housing and enters the upper radiator tank. The tank may be constructed of brass, copper, aluminium, or in modern vehicles, plastic. The tanks are attached to the core, which is a series of tubes separated by heat dissipation fins. In newer vehicles, the core is constructed from aluminium. As the coolant is pushed from the top tank through the core tubes, heat energy transfers from the coolant to the tube walls, then to the heat dissipation fins. These fins are angled between the core tubes, much like the pleats of an air filter, to increase the surface area available to the moving airstream. The heat energy radiates to the airstream and is carried away by the movement of the vehicle or the cooling fans. The water or coolant pump is used to move the liquid through the water jackets to the radiator, and then from its outlet back to the engine. The pump comprises of a housing, shaft, support bearings, seal, and an impeller. They may be belt, chain, or camshaft driven, or in newer vehicles, pure electric. The design of the impeller draws coolant to its centre and is forced to the outer edges centrifugally. A mechanical water pump will only operate when the engine is running. Most coolant pumps are cast with an atmospheric or weep hole that allows any coolant leaking past the seal to drain off before damaging the support bearings. Engine blocks and cylinder heads are cast with galleries or jackets. These galleries ensure coolant is circulated around the cylinder and combustion chambers. Fitted to the engine block and cylinder head are Welch plugs. These plugs are first used to seal the block when the casting sand is removed. The main purpose of Welch plugs is to act as sacrificial anodes. Since the plug is constructed from a combination of zinc and copper, they will corrode before the main engine components. Originally, engine fans were simply attached to a pulley and driven by a fan belt. They had fixed blades and were efficient for early engines. Modern engines require more sophisticated systems. These systems may include variable pitch fans, viscous couplings, or electric fans. Variable pitch fan blades change angle at different engine speeds. They tend to flatten out at higher RPMs, as the higher vehicle speed should be sufficient to supply a steady stream of air through the radiator. Newer fans are constructed of plastic and are designed with the blades asymmetrically placed around the circumference. This reduces blade noise at low vehicle speed. Viscous or fluid couplings rely on engine temperature to operate. At lower temperatures, the fan drive is in a run-free state. So as the engine temperature rises, air passing through the radiator takes on heat. The now hot air influences a thermostatic clock spring found in the fan drive. The spring expands with heat and operates a valve to control a contained fluid flow within the hub. The silicon or viscous fluid is able to change its viscosity with heat and is channeled in such a way that it provides a coupling of the fan hub to form a semi-locked drive. As the vehicle speed rises, the airflow through the radiator is cooler. This has the opposite effect on the control valve and viscous fluid, so the hub is able to free spin. Electric fans are often fitted in single or paired units. These are common in transverse engine configurations and vehicles with larger AC systems. These systems may be ECM controlled. All fans are fitted with a shield or cowl. These are there to direct airflow through the radiator. Cowls should never be discarded or modified. Cooling system hoses are made of a layered and reinforced rubber-based material and are used to deliver coolant through the system. The hoses must be strong enough to contain the system pressure and withstand a very wide temperature range. Some hoses may be found with internal springs that prevent the hose from collapsing when under low to negative pressure. Remember, heat and pressure can be a dangerous combination. So when working around cooling systems, safety must come first. As always, keep training. Thanks for watching.
Okay, that was our video on one of the videos on cooling systems. So I'll just go back to now sharing this PowerPoint presentation that we're working through. You might have seen in that video, we talked a little bit about downflow and crossflow radiators. We also talked about the function of a radiator. It transfers heat from the fluid inside the engine to the air outside, thereby cooling the fluid, which in turn cools the engine. Radiators are often used to cool automatic transmission fluids as well. So within a radiator on your automatic vehicle, there's also another coolant path, if you like, or another coolant or small radiator, let's call it, in one of the tanks that helps cool the automatic transmission as well. Sometimes air conditioner, refrigerant as well, sometimes intake air as well, and sometimes motor oil or power steering fluid in different models can all be cooled through the radiator. Of course, in those scenarios, the transmission fluid and power steering fluid or whatever else is being cooled by the radiator doesn't mix with the water, of course. It stays separate within another cooling system within the radiator. Onto hoses and clamps. As you might have seen in the video, hoses are designed, and they're pretty sturdy things as well. They take pressure, they withstand a lot of vibration in an engine as well, and they withstand a lot of heat and a lot of operating cycles. So they're always getting hot, always getting cold. So when it comes to hoses and your clamps to hold those hoses on, when you're inspecting those, always inspect them for security and general wear and tear and general condition as well. So hoses and clamps are a pretty integral part of a cooling system. We spoke a little bit about coolant. There are many different types of coolant in today's vehicles. It's really important to read the workshop manual to confirm the correct coolant for the vehicle you're working on. We've spoken about the toxicity of coolant, so care must be taken when using that liquid. So wear protective clothing and PPE and read the material safety data sheet for use. Inspecting radiators. So what are the main issues that we look for when we're inspecting a radiator? So what are some of the things that would cause us to want to replace a radiator? So I've got a couple of images there. You can see the top left-hand image there shows a radiator that has some sort of damage or rust, corrosion to those very fine, thin metal parts of that radiator core. That will lessen the cooling effect of that radiator and render it unserviceable if it's too bad. A little bit of damage might be okay. You can see some physical damage there where it's been impacted by probably animals or moths or fly or birds hitting a radiator, or even tools. And some of that damage you'll see is from rust as well. The next image where the man is wearing those green gloves when inspecting the hoses and the clamps and the neck of the radiator for cracks or any damage as well. We're also looking inside the radiator, going down to the bottom image on the left, inside a radiator, you'll often see a rusty looking fluid that might indicate excessive corrosion, might indicate low levels of water, might indicate that the coolant needs replacing as well. And of course, the bottom image there, it's pretty self-explanatory. There's a car that's overheating and steam's coming out. What that means is, steam means there's boiling water, and the goal of a cooling system is to stop that water from boiling. Once water's boiling, it cannot absorb any more heat. Once the water's boiling, the heat's got to go somewhere. If it can't be absorbed through the liquid, then it goes and flows into the engine components, thereby overheating those components, expanding those components, and potentially seizing your motor and causing significant damage to components such as bearings, cylinder heads, and other components within an engine. So the cooling system is always working, and it does a great job in most cases. So what are we looking for when inspecting a radiator and associated components? So first of all, rust and corrosion, damaged fins and a damaged core, any signs of leakage, any signs of physical damage. Had a student the other day, had a car with a crack in one of the plastic tanks on the top of his radiator, was significantly leaking water everywhere once we pressurized it. That was quite obvious. So cracks in plastic tanks is a little bit common these days. In the older days, radiators were made of copper and steel, and perhaps a little bit stronger. Now they're lighter. However, they're made of plastics and they can be prone to cracking. Check the thermostat as well for its correct opening temperature. So we can take the thermostat out. It should have a temperature stamped on the outside of that thermostat, which will indicate the temperature of the water required to open that thermostat. We're checking hoses for leakage, hose general condition. Soft oil-soaked hoses can also cause leakage and bursting. Check security and condition of clamps, check radiator cap seals and general condition, and pressure test system to check for leaks. So there's some of the things to look for when inspecting a radiator and associated components. So steps to removing a radiator. We're just going to go through these steps. The subject that we're discussing now is remove and replace radiators. So I've written down a number of steps required to remove a radiator. So first of all, we might raise and support the vehicle. Now that may be required in some cars and may not be in others, but where you need to get underneath the car and undo lower radiator hoses and potentially hoses that go to the transmission cooler, you may need to get underneath that car. So jack it up, support it with jack stands, put some chocks behind the wheels and put the handbrake on. Step two would be drain the coolant from the radiator. There might be a drainage valve underneath, or it might be that you have to remove the lower radiator hose to drain that coolant. Of course, we're going to contain that coolant. We're not going to let it flow down the drain. That's my phone ringing. Step three, disconnect the radiator reservoir hose. Loosen the hose clamp using pliers or a screwdriver, depending on the clamp design. Disconnect the hose by twisting and pulling it away from the radiator. So these steps would be similar steps you might find in a workshop manual. So if you're looking to remove a radiator from a particular vehicle, always consult the workshop manual and the procedures contained in that manual. I've paraphrased most of those manuals and put these steps in a general sense. But as I say, always follow the workshop manual. Step four, remove the upper radiator hose. Loosen the hose clamps by pliers or a screwdriver, then remove the hose by twisting and pulling it away from the connection. Step five, remove the lower radiator hose. Loosen the hose clamps the same way. Step six, disconnect the cooling fan, electrical connector. Most of the time, these days on more modern cars, they'll have an electric fan rather than a fan belt driven fan. So disconnect that electrical connector. Step seven, remove the cooling fan, mounting bolts. Sorry, I've just shared that screen, or sorry, moved it. So disconnect the fan mounting bolts, remove the fan, and use appropriate tools. Step nine, disconnect the transmission cooler lines. Disconnect the transmission cooler lines from the radiator using a flare nut spanner to prevent rounding off of the fittings, and remove the mounting bolts from the radiator. Remove the radiator bolts using the wrench or ratchet of the appropriate size, and then remove the condenser mounting bolts. The condenser may or may not be on your car depending whether you have air conditioning or not. The condenser would be the air conditioning condenser, which often sits in front of the radiator. It's a separate small or a different type of radiator which doesn't have water flowing through it. It has air conditioning gas flowing through it, but it looks very much like a radiator. Remove those bolts using the correct spanners. Remove the radiator and remove it safely from the vehicle. Clean up after completion. Replace tools and equipment in their correct locations. That's a quick rundown of how to remove a radiator. So what I might do now is I'm just going to share another video with you all, and I'll just go on to Automate now, and I'm going to watch another video on best practice drain and flush. We're going to be talking about coolant systems. Let me just find the right video for you here for a moment. Won't be a moment. Just bear with me for a second. There should be a list of videos here to watch. Cooling system diagnosis, where I best practice drain and flush. Just going to share that screen now. So this is typical good best practice for draining a cooling system in an automotive workshop.
In a perfect world, engine coolant would perform for the duration of the vehicle's service interval. However, with the introduction of long life and ultra long life fluids, there's plenty of time for things to go wrong. If the coolant shows any sign of deterioration, or it's failed through strip, hydrometer or multimeter testing, then it needs replacement. Best practice tells us that coolant replacement is more than just a drain and refill. We need to remove all traces of the old coolant and any sludge from the system. Otherwise, we're just wasting our time and the customer's money. Make sure to wear protective gloves and glasses, as glycol is toxic. Be sure to capture all waste fluid and dispose in accordance with local and federal regulations. A chemical flush solution is often a faster way to remove built-up sludge and debris. Just make sure the one selected is compatible with materials used in the construction of the vehicle's cooling system. Be sure the heater is turned to the hot position before starting the underhood procedure. Let's drain the old coolant at the radiator and at the engine.
So turning the heater to the hot position is going to allow flow through the heater core that sits behind your dashboard, and make sure that all of the fluid that's in that heater core, which is just a little radiator very similar to the one that's in the front of the car, allows that water to be expelled from that heater core as well. So turn it to the hot position before you start your engine.
Engine block. A hose fitted to the drain valve in either case will help prevent spills and unwanted mess. If installed, take this opportunity to remove and wash the coolant reservoir. The flush we have chosen requires us to use the entire bottle. The instructions ask us to mix it with fresh water and then draw it into the system. We should always use a vacuum fill method when replenishing the cooling system. Even if the engine is fitted with bleed valves, this process will help prevent airlocks occurring. Start and run the engine, allowing the thermostat to open. Circulate the mix for the allocated time frame as described in the chemical flush instructions. Let's allow the system to cool and let the pressure drop to safe levels. drain the flush solution from the cooling system, and dispose of in accordance with local and federal regulations. From this point, it's best practice to remove the thermostat and backflush the entire cooling system. This is the best way to remove any remaining impurities and the chemical flush. The thermostat may be located at the coolant outlet or inlet. Once removed, fresh water can be pushed through the system in a reverse direction. This is usually done by removing the top hose from the radiator and then connecting the fresh water supply directed towards the engine. It may also be necessary to remove the lower coolant hose, as this will prevent contamination or debris from blocking the radiator core. The radiator itself can be reverse flushed by pushing water into the lower tank and then capturing the waste from the upper. The heater core can also be reverse flushed in the same manner. Install the fresh water supply into the heater outlet and capture the waste from the inlet. Regardless of how hard it is to access the thermostat, this is the best method for flushing any cooling system. The best way to check for leaks, remove all air, and refill the cooling system is to use the vacuum fill method. Let's drain the system of all flushing water, reinstall the thermostat, and make sure the heater valve is turned on. Connect the manifold with the Venturi adapter and the shop air supply to the coolant filler neck, and then open the valve. These tools work using a Venturi action that create a low pressure within the cooling system. This is how air and any remaining liquid is removed from the engine and radiator. After a few minutes of operation, the indicator on the pressure gauge will stabilise with a negative value. It's quite normal for the hoses to be compressed. Close the valve and remove the shop air. Monitor the gauge for a couple of minutes looking for any movement. If the pressure begins to rise, then there is a leak within the cooling system that needs repair. If there are no leaks, we can begin the refill process. Simply connect the fill adapter to the manifolds with the pickup hose submerged into a container of pre-mixed coolant. When we open the valve, the new coolant will be drawn through the manifold and into the cooling system. Be sure to monitor the coolant level from our supply. If it drops below the pickup, air will be drawn in and we need to start the process again. The coolant flow will stop as soon as the pressure within the system is balanced. This should equate to a completely refilled system with no air pockets. Run the engine until the thermostat opens. Check the fluid level and then complete the road test and recheck for leaks. Flushing and refilling a vehicle's cooling system correctly is an essential part of best practice vehicle maintenance. Don't take shortcuts. It'll only result in reworks and lost customers. Remember to keep training and stay ahead of your competition. Thanks for watching.
Okay, there's our best practice drain and flush method. Some good information there as well. I'm just going to now share the PowerPoint presentation again. We're talking about coolant additive concentration. So we know that coolant by itself can come in a premix or a undiluted solution. Again, look at the manufacturer's workshop manual. The manufacturer itself will describe the required concentration. I've got an example below. The mixture ratio of ethylene glycol depends on the conditions the vehicle operates in, but generally 70% water and 30% additive is sufficient, and sometimes 50-50 mixes in extreme cold climates. So in a very cold climate, we're going to need extra antifreeze effect, so you might need more of the glycol solution to stop that freezing happening. Some engines and systems also require the coolant system to be bled. Bleeding means, of course, allowing all of the trapped air to be removed from the system. There is a procedure for cooling system bleeding. I've put a basic procedure here. It's going to differ for every vehicle that you encounter, but in general, once the engine has reached operating temperature, turn the coolant bleed screw, which is typically on the top of the thermostat housing at the top of the engine, because air bubbles to the top of water. So at the highest point of the cooling system is typically either the very top of the radiator or the very top of the thermostat housing, which is where all the air will ultimately end up. So you can undo that bleed screw, allowing some of that air bubbles to come out, or all of the air bubbles to come out. Don't remove the screw all the way, otherwise you'll have a stream of boiling water coming out, and that will burn you. Once you see a stream of coolant free of air bubbles flowing from under the screw, you can tighten that again. You may need to turn the engine off, wait for it to cool and top it up, and then you may need to repeat that bleeding procedure, but that's one useful way of bleeding the engine. So that is the end of our presentation today on coolants, radiators, remove and replace. There should be sufficient information contained in the document, in the PowerPoint presentation, and the material safety data sheet now to attempt the assessment. I'll pull that up on the screen now. You should be able to log into the Gold Coast Trades College cloud or online system. Go to this assessment tool here, download it to your desktop, answer the questions. It is in an editable format, an editable PDF format. You can answer the questions that are in this assessment. If you need to watch this video again, by all means watch it whilst you have the assessment tool open, and I think you'll find most of the answers will be in my description. Different types of radiators, what's the function of a radiator, what's the function of a thermostat, we've covered those things as well. You may need to do some research, but it's all available to you there within the college cloud. So thanks again for watching today, and remember to download that assessment tool, and once completed, upload it again to the college cloud, and we'll get that assessment. If you're having any trouble uploading it to the cloud, then feel free to email me or email the college with that assessment. And good luck, and we'll see you next time for the next video.